So 5x minus 3 is greater than 45 is an inequality, and we're going to try to figure out what values make it a true statement. Because that's what it means when we solve, guys, right now. Put aside the 24 thought process. All right. As we get started, we need to think about what these three phrases mean, what they look like algebraically and what they look like visually. A number is 5. Could be written how algebraically? How could you write that with numbers, symbols, and perhaps letters? Liam?
5.
Yeah, but what can we do about this? A number is 5 part.
Oh, like W plus 5.
Well, it's not adding 5, it's just the number is 5. So W is 5 could be written how, Liam? Instead of is. What does is mean mathematically? If the number is 5, that means what? Anna? It equals 5. So W equals 5. Logan?
Oh, no, I can't say that.
Okay. So we'll stick with Liam's W now. What about this one? A number is less than 5. Now it doesn't say a number less than 5. It says a number is less than 5. How can we write that mathematically? Mary? Well, that would be if it was a number less than 5. But it's got an is less than. Mary? What, tell me what, if I say a number is less than 5, tell me a number that is less than 5. 4. What's another number that's less than 5? Anna? 2. Michael?
Negative 300.
Negative
3,730.
Great. Yeah, there's a ton of them. How do we write the is less than relationship in mathematics? How do we write that? Jack?
It's like, I don't know how to describe it. It's like, it's like slant.
Which way is it opening?
It's opening to the right.
Yeah, this is what that means. This is a number is less than 5. All right. Now, I started to ask you, well, what numbers were less than 5? And you gave me a lot of different numbers that were in fact less than 5. Because it could be any one of those. When it says a number is less than 5, there's a gazillion possibilities it could be. Could it be negative 1.2?
Yes.
Yeah. It could be negative 1,000,000,000.
Negative 1,000,000.
Right. You got the idea. So we show this graphically on a number line. Part of what we're going to do today is when we solve these inequalities, there's not just one solution, there's a whole bunch of them. So we make a graph to illustrate that. All right? A number is less than 5. Is 5 less than 5?
No.
No. So we can't include 5. So mathematically what we do is we put an open circle on 5. Because that says this statement does not include 5, but it includes everything less than 5. So we shade the number line like that down into the arrow. Why do we have arrows on a number line graph? What do those numbers represent, or arrows representing?
Which way things are going.
Which way they're going? True, but there's something more than that. There's another concept in there with it. Caitlin?
Numbers keep going.
Yeah, they keep going so that we make sure we include Michael's weird 300,000 number or whatever. It doesn't stop short here. Yeah, Luke? Yeah. All right. What about this one? A number is greater than 5. How do we show that mathematically in mathematical symbols? Girl?
W with a crocodile mouth eating the W and then 5.
Okay. W is greater than 5. All right. So we can make a number line. And how would we illustrate which numbers are included in the set of numbers that are greater than 5? Anna?
You shade from 5 to the right to the
Okay, do we include 5?
No,
right? We put a circle around it to say it doesn't actually include 5, but everything up above it. All right, now I'm going to introduce to you an inequality symbol you might not have seen before. All right, and that's what these blanks are for. If I tell you a number is less than or equal to 5, it changes things a little bit. It changes things a little bit. Instead of using an equal sign or a less than or greater than sign, it's actually a combination. A number is less than or equal to 5. See how the symbol changes? It's the less than symbol with a half of an equal sign on it. When you see this symbol, then you need to know that that changes your solution set by just a little bit. How does that change the solution? Mikey?
That means it can be anything higher than 5, or it can be 5 or higher instead of just anything higher than 5.
Right, it can include 5, but this is less than, so no.
Then it can be anything, it's 5 and anything less than 5.
Right. So if we were using an open circle here, what do you think we have to do here to show that it includes 5? Robbie?
Close the circle.
Close the circle, yep. So when you see one of these inequality symbols, you use a closed circle and shade down. This, of course, you can probably predict what you think goes in these blanks right here. Yeah? Or equal. And what do you think it's going to look like? You can probably predict with inequality symbols. Instead of just the greater than symbol, it's greater than or equal to 5. And I bet you can draw your own graph quickly. What would it look like? Since it includes 5, this time you all should be putting a closed circle on 5, and we're equal to or greater than, so going up the number line. Today, when we get done solving inequalities like this, we're not going to talk about our answer just being one value. It's going to be one of an infinite amount of values that make it true. All of the numbers greater than or equal to 5 will make it true. Okay? So let's go on and see if we can come up with a strategy for solving the inequalities. First of all, do they look a lot like the equations we've been solving in recent weeks? Yeah, they do, except for that symbol in the middle, right? So if we could use all those same skills to solve these, that would be fabulous, wouldn't it? So let's see if we can. Okay, so the question we want to figure out is, can we treat an inequality like an equation so we can solve it the same way? Well, let's start by considering something we know to be true. Do you all agree that -2 is less than 6?
Yes.
Yeah, absolutely. All right, so that's an inequality. We know it's true. Let's see if we can add an equal quantity to both sides and it still be true. Because that's basically what we do when we solve equations, right? We add the same thing to both sides and keep simplifying it, right? So pick a small, reasonable number that we could add to both sides of this inequality, Mikey.
Plus 20.
20. All right. So let's see what happens if we add 20 to both sides of this inequality. Does it stay true? -2 plus 20 is what, Daryl? Just this part. What's -2 plus 20?
Oh, negative 18.
Negative or
I mean,
positive?
18, 18.
You know. And 6 plus 20,
26.
okay. Is 18 less than 20?
Yes.
Yeah, that's still a true statement. So we can add something to both sides of this inequality and it'll remain true, just like when we were working with the equation. Yeah, well?
That's what's there.
Oh, 26. There we go, thank you. All right. Sometimes, though, working with negative numbers have a different impact. So let's see if instead of adding Mikey's positive 20, if we could add a negative 20 and we would still have a true statement. -2 plus -20 is what, Logan?
22.
What did you say? -22? And then 6 plus -20, what is that, Anna? -14. Is -22 less than -14?
Yes.
Yeah. Yeah. Okay, that's great. we can do this. We can add the same quantity to both sides, we'll still have a true statement. So maybe we can treat these like equations. We can add things to both sides of it. Let's see if we can multiply or divide things to both sides of it. Oh wait, before we do that, let's talk about subtraction. So, what do you think? Do you think that it'll work to subtract the same thing from both sides? Do you think we'll still have a true statement if we subtract the same thing from both sides?
Yeah.
Yeah? What's a legitimate argument for that, Will?
That equals.
That it'll still work in subtraction?
If you take 20 off from both sides, it would be negative 2 is less than 6.
So if you subtract 20 from both sides, you think it'll still work? Okay, but what's like a mathematical reason that we don't even have to kind of worry about subtraction? Because what do we know about subtraction? Caitlin?
You change it to a formula of addition.
Yeah, every subtraction can really just be written as an addition problem, right? So we don't even have to, we can just say, well, we can change it to an addition problem, so this will work too. We can subtract things from both sides. All right, now let's move on to multiplying. Let's see, if we take this true inequality, can we multiply both sides by the same thing and still have a true inequality? Pick a small reasonable number to multiply by, Will.
1.
Let's do something besides 1.
2.
2. All right, let's multiply both sides by 2. Putting it in parentheses so you don't think it's a subtraction problem. When we multiply 2 by negative 2, what do we get, Luke?
Negative 4.
And when we multiply 6 by 2, what do we get, Mary? Is negative 4 less than 12?
Yes.
Beautiful. That was nice. Yes, Mikey?
Well, I wouldn't necessarily work if you multiply negative numbers because.
Okay, wait.
Okay, flip it.
All right, let's find out what you're talking about, Mikey. We checked the negative number for adding, and it was fine, right? Well, let's check it for multiplying and see. Mikey's looked ahead and discovered, wait a second. So instead of multiplying by Will's positive 2, let's see what happens if we multiply both sides of this by a negative 2. And let's find out what Mikey's talking about. What's a negative 2 times a negative 2, Vaishu?
4.
And what's a 6 times a negative 2, Michael?
Negative 12.
Negative 12. Is 4 less than negative 12?
No.
Problem. We have a problem. Yeah. You multiply both sides by a negative, the inequality is no longer true. We would have to reverse the inequality. If you multiply by a negative, you need to reverse that inequality. Otherwise, it's not going to be true. All right, well, that's a little glitch in our system. Mikey?
Well, it would only really work if they were like two, if it was like one positive, one negative. But if they were both the same, it would stay the same. Like if there were two negatives, then you multiply by it was negative 4, negative 12, and it was greater than negative 12. If you multiply by a negative 2, it would still be the same.
All right, let's talk. I need to convince you about that. So if you said negative 4 is greater than negative 12, you're picking an inequality, that's true, right? And you multiply them both by a negative number. Let's multiply them both by negative 2 again. Let's see what happens. Negative 4 times negative 2 is a positive 8. Negative 12 times negative 2 is a positive 24. Is 8 greater than 24? So it doesn't matter. Anytime you multiply by a negative, reverses the inequality. All right? What about division, though? Because a lot of times we're dividing when we solve inequalities.
So the answer is no.
So the answer, well, is it still true if we multiply both sides? Not if it's negative. If it's positive, it is, but if it's negative, it's not. So it's yes and no. Yes for a positive, no for a negative. All right. What about division? Do we need to divide this both by two sides to decide, or can somebody make an argument like we did with subtraction? Caitlin?
Well, for division, you have to switch the, like when you're dividing two fractions, you have to change the second fraction so the, flip the numbers, then it becomes multiplication.
Yeah, Caitlin's exactly right. Every division problem could be written as a multiplication problem. So the same thought process would hold true here, that if we multiply or divide by a positive, it'll stay correct, but if we divide by a negative, it'll change. And you can do a quick check. Let's take -2 is less than 6. You can see if we divide them both by a +2, we're good to go. But if we divide them both by -2, we get the same issue. All of a sudden we get 1 is less than -3, which is not true. So you would have to reverse the inequality sign when you multiply or divide. Okay? Okay, Mrs. Doble, but I don't know. I believe you. I saw it with my own eyes. And this is getting a lot of stuff, so let's summarize it. Remember, our goal here was to solve the inequalities. So in conclusion, we can solve these much in the same way as equations. First, we learned, or we saw, that you can, what? Blank the same number to both sides of an inequality. It was the first thing we tested, and it worked. Liam? Yeah, you can add the same number to both sides of an inequality, and it works. Then we went on and we talked about subtraction, right? But then we talked about multiplication. You can multiply both sides by the same positive number. That was no problem. Except when you multiply or divide both sides by a
Negative.
negative, good. You must reverse, very good, the inequality symbol. So, okay, we know how to solve equations. We basically know how to solve inequalities. We just got to watch out for that dividing by a negative glitch, okay? All right, so at this point, I hope some of you are thinking, yeah, I saw that, but I'm wondering why that happens. I don't know if I get why that actually happens. So this is a quick little look to see if it makes sense why we have to switch the inequality sign in that situation. If somebody tells you that the opposite of x, is less than 0, it would look like this, right? Here's 0, the opposite of x is somewhere less than it. That's what this statement says, right? Here's what I want us to think about. Where would x be if this is where the opposite of x is? Can somebody come graph it on the number line for me? Or put it up there? Will? This is where the opposite of x is. Where's x? All right, about there. It's the same distance on the other side of 0, right? All right. And we really could find that by dividing by -1, which gives us x. How does x compare to 0 now? The opposite of x was less than 0. What's x do? How does it compare to 0, Robbie?
Greater than.
It's greater than it. So you see, when we're looking at a negative quantity, and then we want to know about the positive quantity, it's on the other side. So it's going to force the inequality to be flipped. All right? So that was just my attempt to try to help you understand why we got to reverse that inequality symbol. But I know you want to get on with just solving them. This is where the rubber hits the road, they say.
I said this is three.
All right. Number 1, -3x is less than -27. This is an inequality. We want to know the solutions. What values of x make this a true statement? Well, it seems like from everything we looked at, we can treat it like we would treat an equation to isolate the variable. So, what do you want to do, Daryl?
Divide by 3.
3 or -3?
-3.
Yep. So divide by -3. So then x, we just divided by a -3. So what has to happen now? Oop,
X has to be greater.
yeah, we gotta reverse that inequality sign. We got that opposite thing going on the other side of the number line. And what's -27 divided by -3, Liam?
-9.
Positive or negative?
Oh, positive.
Positive. So the solutions to this equality are all numbers greater than 9. Now we need you and we require you to graph that so that you think about the fact of what numbers actually make this true. Is 9 a solution to this inequality? What do you think, Jack?
I don't think so.
No, because x has got to be greater than 9. So 9 is not a solution. Robbie?
And then you just shade it to the right.
You shade everything to the right. That's where all of the solutions are. So there's an infinite amount of solutions to this inequality. Can somebody tell me one of the solutions? Oop, 12. Will, what's another one? 9.12. Jack?
5,973.
Yes. And I'm going to keep it simple and say 1,000. Quick check. -3 times 1,000 is -3,000. And it is, in fact, less than -27. So what's the solution to the inequality? All of those numbers, not just one. Oop.
I say one more thing that's greater than
Sure.
pi squared.
Oh, sure, pi squared, 9 something. All right, good. All right, number 2, a little bit more complicated. We're still trying to solve for h. What should we do first, do you think? It's like an equation, treat it like an equation. Mary? -11, yep, add -11. Eliminate that 11. Remember, we can add positives and negatives, and that's no problem. The left side here simplifies to what, Mike? Gotcha.
-18.
Okay, and what about the other side? 2h. So 2h is greater than -18. What do I have to do to solve this for just h, Jack?
Divide them both by 2.
Divide them both by a +2. Is that going to cause any issues with my inequality symbol when I divide by a +2? Nope. So h is greater than -9. Don't have to reverse the symbol because we're just dividing by a positive. No problem. But we do have to graph it. And kids, you need to slow yourself down when you think about graphing this. You got to put the right numbers in the right place. What number is just greater than -9? Luke?
-8.
-8. What number is just smaller than -9, Anna? Okay, so we have our number line set up correctly. The solutions are all numbers greater than -9. What kind of circle should I put on -9? Open or closed? Michael?
Closed.
How come?
Because we're moving backwards. Or the other way around, and it's starting at 9, like including 9.
Okay, does it include 9 when there's no equal to bar?
Oh,
under it?
no.
No. So then what do we got to put on 9?
Open.
Open. Open circle. It doesn't include it. And I think I heard you say shading backwards.
Yeah.
It's all numbers greater than -9. Where are the numbers greater than -9?
That way.
That way.
I know I said backwards, but I thought you said backwards. Instead of like
Yeah.
right or left.
All right, so right up the number line, 0, 100, 1,000, all of those numbers will make it true. Luke?
Wait, what's the difference between the open circle and the closed circle?
It's greater than or less than are open circles because it does not include that value. Greater than or equal to or less than or equal to are closed circles because it includes that value. Right? Look back to the first page of our notes, the first slide we talked about. Back, back, back. Back still. Open circle, closed circle, right? That's the difference between greater than and less than. It doesn't include that boundary point. And the equal to, the greater than, or equal to, or less than, or equal to includes that point. Okay? All right, so we have like 3 minutes. I want you to do 2 problems on your homework assignment. They're not tough, but I just want you to make the connection. So get yourself set up while I bring the worksheet to you.
And someone ate it.
Too much kids.
Oh, someone putting that.